Now this is the 9th question, which is going to conclude our mini-series on the final session. Now we've acquired the state space model in question 8. We've designed a state feedback controller. Now a state feedback controller needs to measure each state. Therefore, we have to have sensors that should measure each state. Now, in some circumstances, it might not be possible to measure all of them, or it might be too expensive to measure all of them. And therefore, we might need to design a structure or come up with an algorithm that will essentially fill in the needs of a measurement. Now, in most of the cases, we are familiar with the fact that we measure the output of a system and use the difference between the output and our reference signal as an error, and our controller uses that error signal. Now, here, what if we come up with a structure that uses the input and output measurements of the actual system and kind of calculates us the states that are necessary for the state feedback controller, so that we have the states available and our state feedback can use those calculated states or observed states, and then we accomplish our goal. So therefore we have this structure called Lindberger Observer, and this Lindberger Observer uses the input and output measurements and will calculate the states or estimate the states. And we will use the estimated states as an input to our actual state feedback controller. So there's an interesting duality between the state feedback controller and the Lindberger Observer, which causes the following. We actually know how to design a Lindberger Observer, but we have to review the duality between the state feedback controller and the Lindberger Observer, because we have the tools to come up with a observer design. So let's briefly dive into it. We have our model, state space model, dx equals ax plus bu, and then we have the static relation cx plus du. Now, we want to emulate the system in order to estimate the states. So what we are going to do is, we know the model, the differential equation, so let's copy that. But, well, if we have the same initial condition, then we would end up in the same output. If we use the same input vector, we would again end up in the same output. But what if this system, so the actual plant here, has an initial condition? Now, the only necessary information is the initial condition. If you know the initial condition, you can rebuild your signal here. Of course, if you have measurement noise and disturbance, that should also be taken into account. Therefore, you still need a feedback sort of, or some information from the actual system should be fed into your model. But still, theoretically and ideally, if you know the initial condition, you don't need anything else. You can just recalculate the route that the system is on. But if you want to acquire, or if this model should match the actual system, we need a sort of a feedback. Now, this is the dual of having open loop control and closed loop control. If you have open loop control, if the system, for example, has gain 0.5 in steady state, what you can do is you can just plug in 2 as an input. So I could just go ahead and apply u equals 2 as a constant into a system which has basically, let's say, s plus 2. So this will eventually get equal to 1. But if there's disturbance, if there's modeling errors, then this will not settle with 1. So there will be a difference. Therefore, I need the output and my input, and then the difference of that. If there's a certain difference, then I should take action. If not, then I'm okay. So this is basically the same. I don't know if my output matches the system's output, but I could assume it theoretically, but it would be better to have the difference of the outputs. So I will then therefore define something like this: y minus y. Of course, I should maybe use underscore for the reconstructed emulator system, sort of. So I need to track the difference of the outputs. Since I have linear systems, if the outputs are different, then the states should also be probably different. Now, so having this information would help me out, and the Lindberger Observer uses this difference and feeds it back to here, to the dynamic equation. So this is basically used to correct the states. And in order to design such L, I need to look for the difference between the states. Of course, the difference between the states does not give me too much information, because I don't really have them. I don't know what x is equal to. But I know what the derivatives of x and x underscore are. So looking at the derivative here, e prime would give me x prime and x underscore prime. So, or in other words, this is x prime, so maybe I should stick with this. So I know what x prime and x underscore prime is. Therefore, I could take this one. So e prime is equal to this one, x prime, minus this one here, minus bu minus this feedback term. So this is an interesting equation because, first of all, bu cancels out. There we go. And then, there's an underscore here. And then I can also see that ax minus ax underscore can also be simplified into a times x minus x underscore. And I have also the static relation between y and x and u, and also y underscore and x underscore and u. So let's use those two. I can plug in y equals cx plus du, and then y underscore is equal to cx underscore plus du. Of course, there's minus because this minus sign here. Now, I can also see that du cancels out, and we're left with this, which is quite interesting because I can factor out c, and what I'm left with is x minus x underscore, and the same goes here. And I know that x minus x underscore is basically the error itself, so we end up in ae minus lce, or a minus lce. Therefore, this is the error dynamic, and if this is another system, and if I stabilize the system, if I stabilize the error dynamics here, what eventually will happen is that E will tend to 0, because that's the definition of stability of an autonomous system. So therefore, if A minus LC is stable, then A tends to 0. This means that x minus x underscore will tend to 0, which also means that x underscore will tend to x. So this is exactly what I want. I want this system to track the states of the actual plant or system. Now, in order to do that, I need to come up with such L that stabilizes A minus LC. Now, that's also something similar and familiar we already know about this. Yeah, maybe not in this format, but if I, for example, take the transpose, which is trivial based on the fact that I'm trying to stabilize this system, if I look at it from a different angle, it will not change. If I take the transpose here, T, let's say transpose, I'll take the transpose of this, and this will move to the front here. They will change basically places. And then also this would give me A transpose and then C transpose, L transpose. So this still doesn't look familiar, I know, but this should. So if the eigenvalues of A transpose, C transpose, L transpose are stable, then I might rename them as another A, call this B, and call this K. And at this point you realize that designing a Lindberger Observer is the same as designing a state feedback controller, which is quite powerful. So we already know the formula for K, so we can use that, but with only one restriction, where instead of using A, we should use A transpose, because that's the duality here. Instead of B in the formula, or wherever we use it, we use C transpose. Instead of K, we have L transpose. So there's quite a nice symmetry between the state feedback controller and the Luenberger Observer. So what we can then do is we can just write down the Ackermann formula. Let's include the -2 or omit it, it depends. So let's have K equals, and I will use it for the formula for a 2x2 system. So that's basically it. The inverse of, and then we have B and A times B, and 10 times PDA. That's basically the formula that we use for state feedback controller design. So let's plug these in. We have L transpose, and then we have C transpose, and then A transpose, C transpose, and then PDA, which is not really that important. You can maybe use PDA and then plug in A transpose. So let's take the transpose of the whole equation, because we want to leave L on the left-hand side. So having taking the transpose of this, you should be careful, because this will move to the right, this will move to the left, and then there will be transpose all over these stuff here. So yeah, at this point it is quite easy to show that this transpose will reduce down to PDA, which is not really that important. But it is also interesting that we can somehow work our way out here and get the following. Instead of having this, we will have something like this. Of course, the transpose vanishes. You can you can prove all the stuff that I'm writing down here, but essentially what you get is you get this. So yeah, PDA here is the poles associated with A minus LC, so the eigenvalues of A minus LC. And then you will have a special definition where we actually look at C and CA, which is the observability matrix, phi O. And as usual, this determines the observability of the system, so you have to look for A and C, and if you can acquire both or all the states using the output is determined by the observability here. So there's also a weaker definition, detectability, but yeah, let's skip that part for now. It is the dual, so yeah. Now we can use this formula, or we can use A transpose, C transpose, L transpose, and the usual formula for the Ackermann formula, and we are good to go. Now, how should we determine the eigenvalues associated with the error dynamics? Well, since we will use the observer for control, the measurement or the emulation should be faster than the control itself. So if we, for example, use the state feedback controller from the previous question, where we had 3.5 as an eigenvalue, so minus 3.5 times plus 1i and minus 1i. If we have such a pole pair, for example, we should calculate the settling time corresponding to this, and then we should, for example, take the 10th of it. So if the settling time of the control loop is, for example, 1 second, we should, for example, choose it so that the observer itself uses 0.1 seconds, so it's 10 times faster or 5 times faster, depends on your setup. So this much time is needed to calculate your states, because the states should be ready when you try to control your system. So they should be faster. So the only restriction here is to choose them faster, where faster is in quotes. It depends on you. So basically just maybe 5 times or 10 times further should be sufficient. So of course, you should try your design. If it's sufficient or not, you should decide based on the results. So now, turning back to the question here, it asks us to design a Lindberger observer. So let's treat this as L transpose, so K equals, and then the Ackermann formula for control design. So the inverse, or let's define this as phi O. Let's define this C times A and take the inverse of phi O times PDA. So then we will take the transpose. Yeah, what should be PDA? Now, let me use run 8 here. We have defined these ones here. So let's take this part. So let's run this part here. Okay, let's comment this out. So we have phi O, which looks like this, and you can see since it's a it is invertible, we can observe the system. Now let's have the poles here, but since we want to have faster ones, let's have 0.35. So yeah, and no imaginary part. So you can have imaginary parts, but usually we don't use imaginary parts here. So let's see if we have this. We need the symbolic S, of course. So what is PDS? So PDS should be 7s divided by 10 plus 49 divided by 400. So let's calculate PDA. And you can see we have a certain matrix. Of course, you can also use A transpose, or just take the transpose of this. So let's use PDA transpose. So yeah. Now, the only thing that is left here is to calculate this K value here. So of course, this this needs to be transposed. We can define L as K transpose, and we should good to go. Now, let's check what the eigenvalue of A minus L times C is. And hope that we did not mess up. So, as you can see, the eigenvalue of A minus LC is 0.35 and 0.35. Now, of course, we did mess up in the sense that dividing by 10 makes this slower. So what we should really do was basically minus 35. That's my bad. So faster means more on the left, not closer to the origin. So let's try this again. Now this is what we are looking at. Because 4 divided by 35 would, for example, give approximately 0.11 seconds. So it's quite fast. Maybe we could use a round number like 20 to have nice values here. So I didn't want to have too large L values, so too fast is also not good in terms of noise, so keep it somewhere between slow and too noisy. So let's have this. So of course, designing this is one problem and testing it is another one. So let's go through our PDF. Now here's a step-by-step documentation. Now we have the original system, and then we also have the observer. Now for the observer, you can use y hat, x hat. Here the difference is x minus x hat, and then the aerodynamics are acquired as this. Now if you take the transpose, as I've done it already, this is also the same as this. So assigning the eigenvalues of A minus bk, or in other words, designing a state feedback controller, is the same as designing a Lindberger observer. Now there we have our Ackermann formula for the observer design, and at least 5 times faster is most of the time used. This 5 is also used in the dominance factor, so yeah, we use it a lot. Now at this point we can see that this is the PDS, and plugging in A, calculating the observability matrix, gives us this. Now if you look for the eigenvalues, you can also see step by step that it is possible to see that they are indeed minus 20 and minus 20. Now at this point I've prepared an example, and you can use Simulink to exemplify and test your state feedback controller. This was from question 8, I guess. Now we have the state space model here. I've used the A matrix and B matrix, but I didn't use C and D matrices because I want to have access to the states. Therefore, what I've done is I have defined my own C and D matrices. If you use C equals I and D equals 0, you get Y equals X. So my outputs are basically my states. And this is also a SIMO system, single input multi-output system. So therefore I have direct access to the states. And using state space in this manner, if you're trying to design state feedback controllers or observers, for example, if you need to access your states, then you can use identity for C and zeros, but you have to be careful of the size here. And my initial conditions are 0, which I'm going to come back at. Now this is the system. Then I have my x's, then I manually generate my output y. And I have my state feedback controller, which directly takes the first state, multiplies it with the corresponding coefficient, and adds it to the other state feedback. And then we have the sum, which is applied to the system, and there we go. Now, don't confuse this with the minus sign r minus y and the error, because it is not the same. And also keep in mind that I have used minus 7.25 in the gain itself. So in order to be consistent with my summing nodes. So now if I run this, I can see that I have a closed loop. So We didn't look at this, but if you check it out, you will see that it is basically this step output here. Now we've designed a state feedback controller, but as you can see, it needs the direct feedback of x1 and x2, which are internals of the system. So we have designed in this question a Lindberger Observer. So let's see how we can utilize that. Now, if you use a Lindberger Observer, stuff can get messy, but what I've done is I have copied the actual system. I have still the output constructed manually, but then I created my own structure instead of using the state space here, because I have an extra correction term, L times y minus y hat, and I'm taking the difference of the output of the system and the output of the observer and multiply it with L1 and add it to the first equation, and multiply it with L2 and add it to the second equation. And those equations are basically the observer states. So dx1 observer is equal to the integral of this, which generates me x10, and I am feeding minus 6x10 to the second state. If you look at the A, B, C, D matrices, you will see why. And I am feeding back to 1 times x2 observer to the first state. The first state of my model does not rely on its own state, so there's no connection there. And then we have the correction term from the differences of the outputs times L1, and then also BU is in here. So there are 3 inputs, they determine the x10. And then the same goes for the x20, where we have minus 7 times x20, which is basically the x2 relating to x2, and then there's the x1 term, minus 6, and they will be summed up here, and then we have the input applied to this state, and then also the correction term, the observer term, basically, L2 times the difference of the outputs here, corrects this state here. So these generate my states. This is basically the dynamic relation here. And I create the output, as I've done it with the plant itself, manually by taking 6 times x10 and 0 times x20, and this generates the observer output. Now taking the difference and then feeding it back in. Now, since I have calculated basically my states or estimated them, what I do is I take k1 times the observer state 1 and k2 times observer state 2 and combine them and apply this into the system. So basically, I'm not, as you can see here, using any of the states of the system, but I use the output. So this is again a complex structure that corresponds to the controller structure, and I have the plant and I'm only looking at the input and output of the actual plant. Nothing is measured in terms of states. The only thing that is measured is the output, as usual, as we do in classical control. Now, if I have 0 initial state for my original system, if I run this, this is basically the output, I guess. So where do we have the output? Here. I'm sorry. Now this is again the same. So we did have this, and the other one generated the same. So this scope and this scope. There we go. There's no difference at all, which makes sense because there's no initial condition. So there's no difference. If I add, for example, a disturbance to the actual system, then it will change. But I can do something else. I can come up to this system here, which is my original system, and I can assign it some, oh, not here, sorry. So I can assign it some initial conditions. Let's say 1. Let's say x1 and x2 starts from 1. Of course, my states don't have initial conditions. So let's run it again. Now we see a bit of a difference here, and the actual input is also a bit different. But let's see what these so this is basically x2. So this connection is not really what it is meant to be. So let's connect this to x1 and let's connect this to x2 here. So these are the original states, these ones, and these should be the states of the observer. So if I run this, I can see that my observer is the blue one, starts at 0, and the actual system state starts at 1, and it quickly, and in approximately 0.1 second or in 0.3 seconds, it tracks the actual state. And this goes also for the second state. Now you can see that my system, my observer, estimates its state starting from 0. It goes too high. It depends on the optimality of your observer design. I've chosen my poles randomly, so I don't expect it to be optimal or to be the best observer, but it still works. After some time, it tracks the state, and then I'm basically using this information to control my output. Now, it would be a bit different if I would have used the state feedback itself. So if I run this, for example, so there's this, but since the observer is fast enough, I get almost the same. So if you can see here, there's almost no difference in the output, so it works practically. And we can see that basically, so this is the output, so we can see basically that there's not that much of a difference, but we used the estimated states to feed back the information and the system. Now, this structure is available if you measure both of them, if you have direct access to them. You have to complicate stuff if you don't want to measure them. But since nowadays we use DSPs and high powered computers, algorithms, discrete time operations are not really that expensive. They are very cheap. So you have high computational power. Why not utilize it if you have a strong algorithm that predicts your basically states? So this was the demonstration of this, and we can also work out the equations here. We have the system itself, we have the observer dynamics and the state feedback controller. So basically we can also get the estimations here. We can see that we can conclude that our system has the same order as the system has, or our controller has the same order as the system itself, because we need integrators for each state to emulate them. We have the correction term, which is a static relation. We have the controller, which itself is an array of p-type controllers, so it's a static controller. But the dynamics come from the fact that we are copying and pasting the system itself. So it is of order n, and the closed loop will be then of degree 2n. So this concludes basically the mini-series on the final session. Hope that you will benefit from these video series, and good luck in your exam.